So you guys know that Chemtech. So you guys know Chemtech, right? If you're a student from DUT, you're a student from MUT. I'm not sure about UKZN, but I'm pretty sure the dynamic is the same. Pretty sure the dynamic is the same. So you guys know that we have something we call. Oh, let me just guys start off with the systems that I'm gonna be teaching here. Multiple phase systems, right? Multiple phase. I'm gonna be teaching you guys multiple phase systems. I hope you guys can see that. I'm gonna be teaching you guys multiple phase systems. So you guys know that with multiple phase systems, it's all about systems in this manner. And this manner, this is what? This is a single phase system, right? This is a single phase system, and then this this is what? Okay, now this is a multiple phase system, right? Yes. So you guys, I'm pretty sure you guys know that all that we're doing here, when we're talking about energy balances and multiple phase systems, all that we're talking about is what you take in is what you take out. What's this side is always what's this side, right? So I don't want to waste much of your time because, as I've said, you guys are writing exams, right? So I don't have to go into details about everything. So maybe next semester I can do all that for you guys. But since I'm trying to catch up with students who are writing exams here, so I'm not going to go into detail with all of that. But what I want to tell you is in these tutorials that I'm going to be teaching today, we're going to be focusing on two systems, right? In this manner. I'm going to be teaching you guys systems in this manner. Right? I'm going to be teaching you guys, sorry about that. I'm going to be teaching you guys system in this manner, right? This manner, this is a distillation column. A distillation column, you find it in multiple phase system, right? The second one is one in this manner right here. This is the second one that we're going to be doing here. Okay. And then enter the plant. Right. This is system number 2 that we're gonna be focusing on in this video right here. Please take notes in this video right here. This is not how far I can go. This is not the only thing that I know. But in this video right here, in this specific video right here, on multiple phase systems, this is the diagrams that we're going to be looking on, right? So I'm going to show you guys the book. As you guys have seen the book, right? So you guys have seen this book, right? So we're going to be jumping into chapter 4, right? Chapter 4, this question right here, sorry about that. This question right here, 4.31, multiple phase systems, right? 4.31. I'm going to be pasting the question so that you guys don't have to, to struggle reading into the statements that are here, right? So yeah. So as I am teaching, I'm gonna be posting maybe a clip this side or that side of the question that I'm reading down, right? So it goes like this. 4.3. I'm sure if you guys, I'm not really sure if like the syllabus this semester is using this book, right? But like, I'm pretty sure everything that you do is universal. Whatever that you will learn in this video will be useful to you, because engineering, Chemtech is universal, right? So yeah, it reads like this. An equal liquid mixture of benzene and toluene is separated into two product streams by distillation. Okay, as I've said, you guys, like I'm gonna be teaching two subsystems in this video right here. It's the distillation one and the one with the three subsystems. The one with the transfer unit, another transfer unit here, and another transfer unit here, and another transfer unit there. All right, so this one is the distillation one, the one that I first started with, right? A process flow chart and somewhat oversimplified description of what happens in the process flow. So as I've said, I'm gonna be posting the clips of what I'm reading right down here, so you guys can see. And then they're saying inside the column, liquid stream flows downward and the vapor stream rises. Liquid flow, as you guys know, the theory of distillation, right? Liquid goes down, the vapor rise, right? Okay. At each point in the column, some of the liquid vapor rises and some of the vapor condenses, right? The vapor leaving the top of the column contains 97% mole benzene, is completely condensed and split into two equal fractions. One is taken off as overhead and the other is taken off as reflux, goes back into the distillation column. I need you guys to know that the distillation column has trays and all that, which we can take from third year students. Third year students, they will tell you that distillation column has trays, but in this level, you guys don't know that yet. So they're telling you guys, you would see the overhead in the upper stream, right? There is a condenser which vaporizes the liquid, right? And then it goes back into the distillation column, right? And then the overhead product stream contains 89.2% of benzene fed to the column. The liquid leaving the bottom of the column is fed to a partial reboiler, right? I can see the vapor goes up. Now we're into the what? Into the liquid stream. The liquid stream goes into the reboiler, right? Okay, where was I? The liquid stream leaving the bottom of the column is fed to a partial reboiler in which 45% of it is vaporized. Okay, cool. The vapor generated in the reboiler, the boil up, is recycled to become the rising vapor stream in the column. Okay, so what does this do? So this basically means that as the liquid stream is going up to be reboiled, when you reboil something, it becomes vapor again, right? If it becomes vapor again, it goes back up to the condenser again, up the distillation column to the condenser again, right? Okay. Where was I? The vapor generated in the boiler is recycled to become the rising vapor stream in the column, and the residual boiler liquid is taken off as the bottom product stream. The compositions of the streams leaving the reboiler are governed by the relation. So they are giving you the relation in the reboiler, guys. So they are giving you the relation in the boiler, and they are telling you that it is YB stroke 1 minus composition. So all of these things is composition. All of these things is what is composition. Sorry about that. And you might ask yourself, why are we using letters B? why are we using, you might ask yourself, like, why are we using letters B and A, C? So as you guys have heard in the beginning, the statement said an equimolar mixture of benzene and toluene. But then at the same time they said benzene is vaporized 97% in the overhead product, right? So we're trying to recover benzene at this point. That's why we are using letters B. B is for benzene. If we wanted to recover toluene, we would have used letter T in that case. So yeah, that's the first thing. And then they are telling you in the reboiler downstream, the liquid stream in the reboiler, we have this relation, right? With this ratio right here. Okay, so that's the first thing. That's the first information. That's like one of the informations given in this case, right? Okay, cool. And now you've been asked why, as I've said, where component B and component XB are the mole fractions of benzene in vapor and liquid streams. And then question number 1 now. Take a basis of 100 mole fed to the column and draw and completely label a flow chart, and for each of the 4 streams of a raw process, column, condenser, reboiler, etc., do the DOF, the degree of freedom analysis, right? And identify a system in which there is only one system in this whole thing that has 0 DOF. If there's only one system that has 0 DOF, that means the rest of the degree of freedom analysis is not applicable. That's actually what that means. So we are going to start as like, guys, I'm gonna like give you a picture of the process, so you guys don't feel like I robbed you of anything. So now we're starting at 4.3. I think this is 4.31, right? This is 4.31, right? So this is what we have. This is the flow chart. This is the flow chart. I'm gonna make sure that you guys see everything that I do. So we have a feed here, right? We have a feed here, and we was told that the feed will take a basis of 100 mole, right? 100 mole, right? And before you do anything, before you write your component balances and all that, just make sure you firstly identify your flow charts first. This is the distillation column, and then this goes out. And I like you guys to just shorten your, because this thing takes turns every time, right? This is what your condenser, right? This is your condenser, the reflux, right? This is what your downstream, the liquid stream. Sorry about that. This is your liquid stream. Downstream goes this way into the boiler, where the liquid boils up, exits as a bottom product, right? Goes this way. And I want you guys to get used to using pointed lines like this every time. Do not construct a line in this manner. No, do not do that. Just always point. Whenever your line takes a direction, always point. Whenever your line takes a change in direction, always point. Right, okay? Because I'm gonna explain later in the video why you should consider giving points to every line that you label, right? So this is your flow chart in this process. This is I'm not gonna write the words, but like this is the distillation, right? Distillation column, right? The one that has trays and all of that. This is the condenser. that vaporizes gives 97%, and then a reflux that goes back to be distilled, right? And then a reboiler, right? Okay. And then here we have to take into consideration that we're going to do an overall of this whole thing, overall of the distillation, right? Overall of the condenser, overall of the reboiler, right? So we're going to have 0. Okay, wait a minute. So they explained, they showed in the picture of the whole thing, right, of the whole process, like what was going on. So they showed that you have 0.50 mole benzene per mole, right, and 0.50 mole of toluene per mole. So this is your mixture as a whole that entered the distillation, right? And then this is just like the information that you're given. Everything that you have to put in here, you have to think about it. It's like your own efforts. This is not, it's incomplete in this way. It's incomplete. This is just basic information that was like posted to you, right? Okay. So now you have to decide. You look at your problem statement again. So the problem statement says the vapor leaving top of the column, it vaporizes at 97% and goes back to the reflux. So we're gonna assign values now. We're gonna assign, let's call them N1. So this is your first mole. This is N1 mole. And we know that in this N1 mole, right, we have component balance of what? Of 97%. Mole benzene, right? Obviously, if you do your calculations right, you see that this is 0.3 mole, right? Take 1, you do this is obvious, right? Okay, rise to 0.03 toluene. This is toluene. That's how you find. So right, I have already like done all this question, like just in the morning I've done them. So I'm just gonna look here so that I won't waste too much time trying to I'll just look through here where I've written. And then the next thing that you have to do is what? Is assign okay, first of all, guys, they told you that this stream, right, split into 2. So if this is N1, then this is also N1, right? If this is N1, then this is N1, right? So component balance will be the same. There's nothing that will change here. This is 0.97. This will also be 0.97 and 0.03 mole toluene per mole, right? Okay. So twice of this thing is what? Twice of this thing is 2 and 1 mole. This thing is split into 2, so this is twice this, right? Okay. Obviously component balance stays the same because it's the same stream. Nothing really happens. It's the same stream, so component balance here is still the same. 0.03 mole toluene per mole. So we are done with the vapor stream now, right? The vapor stream, the condensed stream, then to the reflux, and then now we're going to the liquid stream now, because remember, this is an equilibrium mixture of vapor and what? And liquid, right? So if this is N1, then this is what? This is N2. So now we have N2 mole, right? I don't want to rush into putting component balance for this right here. I just want you guys to first, if this is N2, then that means this is N3, the bottom's product, right? So here, what I want you guys to know is that this is the same stream, right? This is the same stream, but then it also splits it. This, if you add these two, it equals to this, right? So what we're gonna have here is, we were told that in the reboiler, wait, this is C for condenser, reboiler, D for distillation column. So it was told in the reboiler, what happens here? The liquid stream is vaporized back here. This is vapor. This one continues as what? Bottom's product, as a liquid for what? For benzene and toluene. So vapor, we use letter Y, right? For liquid, we use letter X, right? So that like I'm getting to where I don't want to confuse these two, because this is still a liquid and this is still a liquid, but then this is a vapor, right? So I am going to assign component balance for this as X, component balance for this as Y, because we are obtaining this the overhead product, that is what? 97%. We were told it's 97%. So we're looking for toluene. We are prioritizing toluene at this point. So this is going to be, I mean, we're prioritizing benzene, not toluene. XB mole of benzene per mole. Obviously, if you want to find this, I don't know if you guys can see that, but it's 1 minus X mole toluene per mole. It's the same thing that you do here. If you want to find this, you have to say 1 minus this thing right here, so get that one, right? So this, because this is a vapor, we're gonna use Y, component of benzene per mole, 1 minus component of benzene, component of toluene, sorry. So this will be our N4, right, mole. But then at the same time, we was told that at what percentage was this recovered back as vapor? It's what? At 40, forgive me for handwriting, 45%. That's 45%. And at what percentage was used up of benzene as overhead product? We was told that we have 89.2% that was used up. So 100 mole entered, but 89.2 was used up. Please keep that in mind. So now I am coming back to my I'm coming back to my conversation, right? So I told you guys about whether about this thing right here, about using letters, right? So I told you that this is a liquid stream, this is a liquid stream, vapor stream. This is not the same as this. So I have to use, wait, I have to use a different letter for this one right here. I have to use a different letter, because if I use the same letter as in this, so I mean this, that will mean this entry is equal to this end, so which is false. So I have to use a different letter. We'll assign it as letter Z. So this will be letter Z mole benzene per mole. 1 minus Z toluene per mole. I don't know if you guys can see that, but yeah. So this component right here is equal to that component plus that component right here. So yeah, I hope you guys hear what the point that I'm reading here. That I cannot assign the same component balance letters, because that will mean this here is equal to this here, which is not, because this stream alone is equal to both of these streams. That's like basic Chemtech knowledge, right? That's like basic knowledge. So yeah, this is your flowchart right here. That's question number 8, right? That's your flowchart right there. And then you guys know we have overall, and then let me use a different marker for that one. Okay, let me use a different marker for that one. So now I'm going to assign my overall. So this is my overall, right? My overall balance, right? This is my overall. I hope you guys are taking notes of that. This is my distillation, right? This is my condenser, right? And this is my reboiler. So that's my flowchart. This is the complete flowchart right there. That's the complete flowchart right there. Keep in mind, guys, there's so many important things they said in the statement, that this stream right here splits into 2. So you're gonna have 2 and 1 here. Split into 2 and 1 and 1. Component balance is the same, but not in this case, because look at here, whatever vapor that comes this side, that goes out this side, that's the same one that goes back to reflect. But then this is a liquid. Whatever liquid that goes this side is not the same as the one that goes back to being retracted back into the distillator. So you cannot have the same component balances here. That's why we are assigning different letters, so that it cannot be tricky. I hope you guys are writing this down, the whole thing. Or maybe I should assume you guys will hit a pause so that you'll see the whole flowcharts of this thing. So now we're done with the flowcharts, right? And then we have to do degree of freedom, right? Analysis, right? I'm going to wrap off all this. So now they're saying do the degree of freedom analysis. Do the flowcharts and do a degree of freedom analysis until you get one with the correct DOF or with the applicable DOF, right? Yes. And as I've done this question, it's only one that has an applicable DOF in this case. All the other ones have greater than 0 DOFs. So this is how it's gonna go. So we start with the overall. I will assume you guys have written down the flowchart, right? I don't have a flowchart right here, but I'll assume you guys have written down the flowchart, right? So we'll start with the overall. We will start with the overall system, right? With the overall system, and I've always told students that, like, they know students from 2023, I think, yeah. I was teaching students from 2023. I was telling them the tricks that you need to use when you do a of analysis and all of that, you do not have, okay, you don't really have to start with the unknowns. Please take this into consideration. You do not always have to start with the unknowns. You can start with the unknowns if you are brave, yeah, but like you will make a lot of mistakes if you do like that, if you do that, you know. So you start with the external information first, and then you go upwards. So start with the external information. So we were told, so this is the overall. So in the statement we were told that there is and the overhead product stream. So I have always told students that start with the external information first. So we are being told there that the overhead product contains 89.2%, right, of what? Of benzene fed back to the distillation column. So as you guys have seen in the what overall system, we cut through N1. We cut through N1, and N1 is the overhead product, right? That has 89.2 fed back. So we have an additional information of minus 1 additional information, 98.2% of what? Benzene, right? What else is external that we have? We do not have anything external except at the reboiler. At the reboiler there is another external info, which is that 45%, whatever. I'm gonna look back to it, but at this point we have this external info. Do we have anything external in the overall? No. We go back to watch how many balances do we have. On the overall we have 2 with toluene and benzene, plus and minus 2 balances, right, which is benzene and toluene. If there was water, there would have been 3, benzene, toluene, water, but in this case, no. Is there anything else? No. And then you conclude and say this, you have minus 2 minus 1. So what does this give you? This gives you minus 3. Whatever thing that you get up here must not be greater than this. If you suspect it with this, it might be equal to 0. So what does that mean? How many unknowns do we have now? Do we have to get in the overall now so that this equals to 0? We have N1, we have N1 in the flowcharts. You guys go back to the flowcharts. You have N1, N3, and XB, component balance of N3. We have 3 unknowns, N1, N3, and XB. So it's 3 unknown variables. You guys go back to your flowcharts then. We have 3 unknown variables, N1, N3, and XB. So now you have equals to 0 DOF, the overall, right? And then we're done with the overall. We're gonna do the distillation one. So keep in mind that they asked you until you find one that has 0 DOF. So at the moment overall has 0 DOF. At this moment overall has 0 DOF, right? So we go to the distillation. In your flowchart, go to the distillation. Distillation column, right? Distillation column. So in the distillation column, again, you go to your flowchart again and assign things. You first again start with any external info that you can get on the distillation column. So is there any external info on the distillation column? No. You only have just minus 2 balances, right? You have benzene and toluene. Anything else? No. There is no whatever conversions happening, no. So you have how many unknowns on your distillation? N1, you have N1. On your flowcharts, you have N1, you have N4 coming as a reflux, you have N2 coming as a downflow stream, right? You have YB, which is a vapor, YB. You have ZB. So you have like 5 unknown variables. So you have 5 unknown variables here, which is N1, N2, N4. Sorry about that. YB. So on a DOF, what does this give? So this is 5 minus 2, which is 3 DOF, of which we do not want anything greater than 0. So this one is not applicable again, right? So we move on to the next unit. The condenser or the boiler, you choose. Condenser or the boiler, you choose. So yeah, so we're gonna go to the condenser now. Condenser, okay? So on the condenser, you look again, is there any external info that you can get on the condenser? No. On the condenser, you just have a single stream that is split into 2 components. Balances are all the same. So what do you have? You have 0 balances. There's nothing to balance there. You have 0 balances, right? But then you do have an unknown or an unknown variable. One unknown variable, which is the N1 that splits into 2, right? So what does this give you? This is give you 1 minus 0, which is 1 DOF. Again, condenser is not applicable, right? Again, the condenser is not applicable. Now we go to the last one, the reboiler, right? Now we go to the last one, the reboiler, right? So in the reboiler, so in the reboiler, is there any external info? Yes, there is an external info in the reboiler. We were told that there is 45% vapor that is reflected to the distillation, right? And then you have also the ratio that I showed you. The ratio, the 2,25 ratio that I showed you. So you have 2 additional informations on the reboiler now. So you will have more time that if you like, you can just name them one by one. But I'll just say I have 2 additional information now. I have minus 2 additional information. Which is the 45% and there was the ratio of 2,25, right? Is there anything else? No. Now you have, how many balances do you have? You have 2 balances, right? You have benzene and toluene. Right, let's do all this. What do you have here? You have -2, which is this is -4. Anything that has to go here has to equals to 0. If it doesn't equals to 0, that means you did something wrong, or that means it's not applicable. In this case, they gave us a hint. They said it's only one that is applicable. So far, the only DOF that we got applicable that had 0 as the overall. So assuming that, so this will not be 0. Okay. So how many unknowns do we have in the reboiler? So we have 6 unknowns in the reboiler. We have N2. We have N2 as liquid, ZB, right? We have N3 XB, that's 4. We have N4, that's 5, and what is that? Vapor YB, 6. We have 6 unknowns, right? 6 unknown. I have to be faster. 6 unknown variables. I have to be faster. ZP N4 YB N3 XB. Okay, so that's it. So what do we have here? We have 6. This is 6. We have 2 DOF, right? Which also is not applicable. So the statement is true. Only one is applicable in this case. So yeah, we are done with number A. I hope you guys get this book. I hope you guys will definitely get it. Even if you guys can like just comment on this comment section below and give me like question papers that I can do. I'll do them. And then I don't know. I'll drop my Instagram handle so you guys can follow me there. So you can DM me there like the question papers you want me to do. Because like I feel like if I drop my personal info here, it's gone. Anyone can call me, and I don't want that. So, yeah. So yeah, so we go to number B now. So number B says, write in order the equations you will solve and determine all the unknown variables on the flowchart, setting the variable for which you would solve in each equation. Do not do the calculations in this part. Okay, so now we are on number B. They're saying use what you have and do do a skeleton of your calculations. Do not do the calculations, but do a skeleton of your calculations, right? So we're gonna start with the overall system again. Okay, we're gonna start with the overall system again. So in the overall system we have 100 mole, right? N1 plus N3. So this is the overall, right? And then we're going to have sorry about that. I want to explain something here. So they are saying do a skeleton of your calculations, right? So if we look at our flowcharts and our DOF that we did above, the only applicable system is the overall system. The rest is greater than 0. So we're not gonna do the other ones. It's unnecessary. So we're dealing with the overall only. So this is the first thing that you need to do, overall system. And then on the overall, what else do you have? You have the 89.2% recovery of benzene, right? Recovery of benzene, right? This is what we're gonna do to solve for N1 or N3, right? Now, to get recovery of benzene, that means we need to find N1, right? That means we need to find N1. So how are we going to find N1? with the recovery of benzene. So remember that I said in is equals to out, right? Remember that I said in is equals to out, right? So that's just the basic of it. So in the recovery of benzene, the one that was recovered, that reacted, in other words. So this will be 100 mole times component of benzene 0,0515, right, times this 89 plus 0,892, right? This is the one that reacted, right? And then the outside one is 0,97 times N1. This is what we're gonna have, right? Because in all of overall we have 3 unknowns. We have N1, N2, and a component of N3, right? So this is the step to finding everything in this overall. To get the reacted modes of the overhead that we found in the overhead, we have to find the percentage that we lost. This is the percentage that we lost, right? But at what cost? At this 0.97 times. Yeah, right? Okay, I hope you guys wrote that down. Okay. And what's the next step? And then the next step is doing the benzene balance. The next step is doing the benzene balance, overall benzene balance. So it's gonna be 100 mole times 0,0515, right, equals to N1 times 0,97 plus N3 times its component balance of what? XP. As we said in the overall flow charts, this is what we're having right now. So these are equations. This is the skeleton of equations that you need to have in order for you to find solutions. This is all they asked. They didn't ask you to calculate all these values in B, question number B. So that's it. That's the answer for question number B. So we're moving on now. I'm running out of time. So we're moving on now to number C. I didn't know that these questions take such time now. This is 3.1. Now we add to number C. So they're asking me, so now with number C they're saying calculate the molar amounts of the overhead and bottoms, right? And the mole fraction of the benzene in the bottoms and the percentage recovery of toluene in the bottoms product. Right, okay, cool. So now what you need to do is take the skeleton information that you did in B and now calculate them. Don't just write them there. Now you need to calculate now. Just take the things that you did on the skeleton. So what did we do? So first of all, we said we have 89.2% of what? Of benzene recovered. We have 89.2% of benzene recovered, right? This is the first thing. This is one of the things we did on the skeleton, right? So what did we do? We said 100 mole, okay, times 0,0515 times 0,892 equals to 0,97 times N1. And then you divide all these things, divide all this, and then you find that your N1 is, punch your calculator, and then you find that your N1 is 45, okay, 45,98 mole benzene in the overhead. This is the moles of benzene in the overhead. That's the moles of benzene in the overhead. Now we want the moles of benzene in the bottoms product. This was the overhead, the one that was condensed. Now we want the one that is a liquid. Okay, what's the second thing that we did on our skeleton? Okay, I feel like this video is gonna be 2 hours or 3 hours, because I'm still gonna do example number 2, and then from there I want you guys to like recommend questions for me to do in this book, or just send me question papers. Just recommend question papers, you know, and go and DM me on my Instagram, Brandon RC. I'm gonna explode it here. Yeah. What's the second thing that we wanted to do? We said 100 mole equals to N1 plus N3. We already have this, right? We already have this now. So this is 100 minus 45, what was it? 45,98, right? 45,98 equals to N3. So now our N3 will be, you punch your calculator and then you get that your N3 will be 54,02 mole bottoms, right? 54,02 mole bottoms. We're finding everything that we did on the skeleton now. And another thing that we did on the skeleton was the modal benzene. We said unknowns were N1, N3, and XP. Now we want to find XP. Okay. Now I want to find XP. What did we say? We said so now this is how they write it. They say benzene balance. So it's 100 0,0515, right, equals N1 times 0,97 plus N3 times XP. So if you look at this, we already have this, we already found this. We're looking for this one right here. So what do? We say XP equals to 100 times 0,0515 minus N1 was 45,98 times 0,97, all divided by N3, which was 54,02. Now you will find your XP. And then as I have already done this in the morning, found the XP was let me just do this right here. So XP was 0,0995 mole benzene per mole. So obviously you can just round this off, right? You don't have to write all the decimals right here. Just round this off and put 0,10 mole benzene per mole. Right? So we found the mole fraction of the bottoms products now. Right. So yeah. So that's basically how you do 4.31. Right, that's basically how you do 4.31. Yeah, so now I'm going to do 4.33, and after 4.33 I want you guys to like recommend, if you guys are using this book in your syllabus, recommend questions that you want me to do, recommend like tutorials that you want me to do on this book. If you guys are not using this book in your syllabus, give me like question papers or give me whatever you guys are doing in your classroom and send them to me on my Instagram. DM me on my Instagram. I'll leave my Instagram handle right here. DM me on my Instagram. Give me the question papers like you guys are doing, or the links to you guys whatever are doing, so that I'll do them and post them here. Yeah, I think that will work. Okay, so yeah. So now we're going to do question 4.3. Remember when I was starting this video, I said we're going to do like multiple phase systems in this video, right? So now we're dealing with a system in the manner that I was telling you about, right? In the manner that I was telling you about, this one right here. So now we're dealing with a system in this manner now, okay? And keep in mind, these like exam type tutorials. This is not just some easy stuff, you know. This is like some exam type tutorials. So yeah. So what is high? And again, I'll post the question here so you guys can see. A stream containing 5 of chromium is contaminated in the wastewater from a metal finishing plant. The wastewater stream is fed to a treatment unit, right, that removes 95% of the chromium in the feed and recycles it to the plant, okay? The liquid stream leaving the treatment unit is sent to a waste lagoon. Okay, a waste lagoon is like the end point of the process, okay? Right. Okay, the treatment unit has a maximum capacity of 4,500 kilograms of wastewater per hour. So what they mean by maximum capacity, they mean the amount of mass flow rate they can withstand cannot be greater than 4,500, right? Okay, if wastewater leaves the finishing plant at a rate higher than the capacity of the treatment unit, the excess, anything above 4,500, we bypass it so that it goes down the other routes, right? Bypasses the unit and becomes with the residual liquid leaving the unit. And the combined stream goes to the waste lagoon, okay? Anything that exceeds the whatever limits we set, it just goes downstream. It joins to the lagoon, right? Yeah, so question 1, assuming a basis of calculation. Okay, without assuming basis of calculation, draw and label a flowchart for this process. Okay, as I've said to you guys, this is how it's gonna be, right? This is basically like how we're gonna do it. So we have a stream, and then, right, I want you guys to okay, I just want to make it like this is a treatment unit. This is the treatment unit, right? So I was told that there's something that goes on like this here, that if I want to, I can just do it like this and just do it this way, right? And I was told there's an excess amount of this chromium liquid, so it was bypassed, and it conjoins the what what is it called, the lagoon waste. So this is how it's be. This is how this whole flowchart will be. But then I do not want you guys to draw it this way. For extra marks, do not draw it this way. Let me just wrap the whole thing. But that's the flow charts. But like for extra marks, do not put it that way. Just do it like this, because every time a stream splits, it's like there is a process unit that splits the stream, right? It doesn't just split by itself. So this is the major process unit, right? And then the streams again goes like this, bypassed, right? Bypassed, right? Yes. And then it goes to the lagoon. So this is the proper way of doing the flow charts. Do not do it like the previous, because you're not gonna get so many marks, okay? So this is the major treatment unit, right? Yes. So the flow chart is incomplete here. So now we was told that anything that enters the treatment unit cannot be greater than 4,500 kilogram per hour. Cannot be greater than anything that enters here, cannot. So obviously we have a mass flow rate here. We're gonna call it M1. We have a mass flow rate here, and we was told that its component was 0, 0,0515, right? 0,515 kilogram of what? Of chromium per kilogram. And then you do your balance, right? 0,515, right, equals to 0,9485, right? So you do your balance. So 0,9485, because it's mixed with water, so that will mean water, right? And then whatever that we have here, we call it M2, right? Kilograms per hour, right? This is like the same stream, but then it splits, okay? There is no mixer, no whatever. It's just the same stream. It's just they added a bypass. So we're gonna give it letter B for bypass. This is a treatment unit, right? Okay, kilograms per hour. Still the same. Excuse me. Still the same component balance of chromium per kilogram and 9485 kilogram of water. So this is how this is the same stream that it was. Well, it's like the difference between like a mixer and a bypasser. A bypass is like a same stream, but it's just taking another direction. But a mixer, it's mixing two different things. So that's the difference. So this is still the same stream, right? 0,0515 kilogram of chromium per kilogram, right? And 0,9485 kilogram of water per kilogram, right? And then they tell me ukuthi kune amount of chromium. They tell us that that recovers 95% of chromium. So that removes 95% of chromium. So this is what the stream did. This is kilogram per hour. So I was told external info, 95% of what? Of chromium, right? Okay. So obviously here there is one that goes to the lagoon, which is M5 kilogram per hour, right? This is still the same stream, so here I have my own components, which are, I don't know, unknowns. Kilogram, kilogram. If you want to get this, you have to minus by 1. Water. I don't know if you guys see that. And then the one that goes to the final one, this one is mixed. This is the final one that goes to the lagoon. The lagoon is that side. It's like a plan. So we want to name this X6 chromium 1 minus X6 a kilo. Okay. So this is the flow chart right here. So this will be a flow chart right here, right? So, okay, wait. Let me remove this. So this will be a flow chart right here. This will be your overall, right? Your bypass, obviously there's nothing you can do with your bypass. And then this is your mixer. This is your mixer. Right, so that's your DOF. That's your flow chart right there. So that's your flow chart right there. I hope you guys wrote it. If you don't see clearly, you'll pause the video, right? So yeah, that's your flow chart right there. Okay. Okay. So let's go to B. So at B, they're saying wastewater leaves the finishing plant at a rate of, so now they are giving us values now at a rate of, so like on your flow chart, wastewater is coming to the treatment unit, right? So it is leaving a plant. This side there's a plant, so there's a stream coming from a plant this side, which is M1, right? So they are saying it arrives at the treatment unit. It arrives at 6,000 kilograms per hour, right? Calculate the flow rate of liquid to the waste lagoon M6, the ones there at the end, to the waste lagoon M6, and the mass fraction of chromium in the liquid as X6. Okay, fine. So now we're supposed to calculate the final answer of the stream that is coming up this side. So now they are telling you that they're giving us assumptions. So they gave us assumptions, yeah? So they gave us assumptions. They said M1 equals to 6,000 kilograms per hour, right? So if M1 is equal to 6,000 kilograms per hour, well, then on your bypass on a flow chart, we can do a balance. So you now say your bypass balance, right? So on your bypass balance, what do you have? On your bypass balance, you have M1 equals to M2 plus M3. Let me put 3 correctly, okay? M1. So now I've already been told that this coming from a plant, right? It arrives at 6,000 kilograms per hour. 6,000 cash. I don't know what merit with this. 6,000. M2, I was told that the maximum capacity that enters the transfer unit cannot exceed 4,500. So what does that mean? We assume that M2 is equals to 4,500. 500 kilograms per hour. We assume that M2 cannot exceed this number. So M2 cannot exceed that number. So M2 is 4,500. So now present 3. Sorry about that, present 3. So M3 is equals to 6,000 minus 4,500. So M3 is what? 1,500 kilograms per hour. Right. Okay. I hope you guys took that down. If you do not understand, we are free to DM me on Instagram and ask me questions. So now we found M3 and what's in the flowchart. So now we are going to the 95% removal. 95% removal, that's right, because on the flowchart, remember, we found M1, we found M3. We assumed that M2 is what? Is 4,500. Now we want to find M4. So the only way to find M4, take this 95% reacted or removal. So now, what do we know? We know that in order to find what exited the transfer unit, we need to take into account that what entered the transfer unit was 4,500 multiplied by component balance for what? For chromium was 0,0515. At what percentage did it react? So that only 95%, there's only the 95% removal at 0,95. So now we're gonna find what the amount of N4 it is that we have. So you type this on your calculator and you're gonna find that you have 220.16 kilogram of chromium exited the transfer unit. So what does that mean? This means that 4,500 entered, this 2,200 left the transfer unit, so like 95% of it. Okay, so yeah. And then what's next? We're going to find M5. We'll find M4 now. Now we're going to find M5. As you already know, the simplest way of finding M5, transfer unit balance, right? On the transfer units balance, you have M2 equals to M4 plus M5, right? So you have M2 as 4,500, M4 as 220.16, M5. So what do you get? I'm not gonna do all the transposing things, you're gonna do that on your own, but you get 4 and 7.84 kilograms per hour enters the mixer. To the mixer. So 4,279 goes to the mixer, right? And then we are on our way on finding M6, right? To the lagoon, right? We're on our way on finding M6. So now that we know, what is M5, let's do the chromium balance, because we also have an unknown of what? Of chromium there. We have M5 and the remember on the flowchart you have M5 and the chromium balance of what? X5. So now let's find the unknown. Chromium chromium balance, right? If you want the chromium balance, you have M2 multiplied by 0,0515 equals to M4 plus M5 times X5. So you guys are going to substitute all because we already have all this. Let's divide all this. We already have all this. So M2 we already have to 4,500 times 0,0515, right, minus what is M4 was 220,16. What was our M5 was 4,279,84, right? Hope you guys are seeing that. And that's your find that your chromium was 0,00271 kilogram. Right, so this is this is your chromium now. Right, I don't know if you guys see clearly. Right, I recommend the better handwriting on the next video. Okay, if you guys don't see. So now we're done with the chromium balance, right? So now we're finding X M6 to the Lacoon, right? So what is your M6? So we're going to sorry about that. So we're going to say mixer balance. Remember on your flowcharts we have all these things. Sorry. So on the mixer balance on the flowcharts, it says M5 plus M3 equals to M6. So what is this? So M5 is 4,784 plus M3, which was M3 was 1,500 equals to M6. So M6 from our Lacoon, what gives us 5,779.84 kilogram per hour to the Lacoon, right? This is how we find M6 to the Lacoon. That goes straight to the Lacoon, right? Fine. And then now we find the component of the stream that goes to the Lacoon, which is X6, right? Which is X6. So that component again is like chromium balance again. So it's M5 times X5 plus M3 times 0,0515 M6 times X6. So this is basically how it's gonna be. So now again your X6 will be divisible by what's going on here? M5 times X5. You guys will substitute the values here, right? Plus M3 times 0,0515 divided by M6. You guys will substitute the values here because we've already found them, just to save time. X6. So we found that when you substitute all these values, X6 will be X6 will be wait. Okay, so when you substitute your values, you will find that 0.0154 kilogram. So this is your x6. Did I write that? I don't know, but I hope you guys can see this is your x6. Right, and then we're gonna end that number, C, because like number C is like a table, right? Number C is like it's the last one for this video. Number C is like a table, okay? Number C is like a table. So this is how we're going to do number C. So at number C, they're asking you like, calculate the flow rate of liquid to the waste lagoon. It's like we are restarting the process now. When the mass fraction, and the mass fraction of the liquid for when M1 is no longer 6,000 now, M1 is 1,000, up to 10,000 in 1,000 kilograms per hour in increments. You plot X6 versus M1 for a graph, okay? Now M1 is no longer 6,000, it is 1,000. Find all the things that you found, but using 1,000. That's basically what this question says. Remove the 6,000 that you were given in B and place 1,000 now. But do that table from 1,000 to what? To 10,000. So this basically saying this is how the table is going to be. This is how the table is going to be. You're going to have M1, right? M2, right? M3, M4, M5, X6, M5, X5, sorry, M6, X6. So this is how the table is going to be. This is how the table is going to be. It's going to be in this manner right here. This is how the table is going to be. Right. This is how the table is going to be. So about that. So you start from M1. They told you that it's 1,000. Right. Starts from 1,000. I don't know. I should write with 1,000. Obviously, if M1 is 1,000, then M2 is also, because the bypass doesn't change anything. M2 is also 1,000, right? So you start this from 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000. Because of space, I'll end at 7,000, but like, this is how it should be. You would end at 10,000, right? So, this is how it's gonna be. They told you that at the transfer unit, right? The stream that comes at the transfer unit cannot exceed 4,500, right? So it's still right here, it's 2,000, it's still right here, it's 3,000, it's still 4,000, but then here it cannot be 5,000, so it ends at 4,500, ends at 4,500, ends at 4,500, right? So so what does the rule say? This is the string that answers, right? If you add M1 plus M3, you get M1. If you add M2 plus M3, you get M1. So a number that you should add that would give you 1000 here, if we have 1000 there, is 0, right? A number that you add that will give you 2000, if you have 2000 this side, is also 0. The number that you add on this string, if it is 3000, to get 3000 on this side, it is 0. The number that you add on this string to get 4000 on this string is also 4000 again. But then the number that you will add here to get 5000, because this is M2, 4000, 5000 plus M3 gets 5000. What is that? 500 gives you 5000, which is the stream 1, which is M1, which splits into 2 by bypass, right? The number that you will add here to get 6000 is what? 1500. The number that you get here to get 7000 is what? 2500. So this is basically how the graph will go, but like I'll do a separate tutorial video on this one if you guys want me to do this one, because like of time I have to end here. But I hope you guys like see how this graph is gonna go, right? So let me just do M4 and M2000. So if we have one to find M4, go and do your what? Go and do your that percentage balance I was telling you about. That 95% chromium balance I was telling you about to get 48,93. I don't know, like I'll do a separate video so you guys will know how I got this. Yeah, so like I hope you guys like enjoyed the video. No, I hope you guys like enjoy these tutorials. I'm like, if you're not using this book again on your syllabus, please send me the book that you guys are using and send me the tutorials in that book so that I'll do those tutorials. Or just send me your question papers so that I'll do the question papers you guys refer me to. So yeah, this is like the end of the video. Yeah, hope you guys like learn something. This week I'm still on multi-phase systems, right? I'm still gonna do some more multi-phase systems if I have time. I'll try to do the rest of the syllabus in a short space of time, because like I didn't know you guys were writing exams already. So yeah, give it a thumbs up, guys, subscribe, yeah. I'll see you on the next video. I'll be talking about combustion reactions. If you guys want me to do multiple phase systems, just DM me on my Instagram. I'll do the multiple phase systems again. Recommend this book right here. If you guys are not using this book, give me the book that you guys are using so that I'll do tutorials that you guys ask me to. So yeah, thank you so much. Yeah.